researchers working on the Large Hadron Collider began peering into a just-opened data cache. This huge machine at CERN, the European Laboratory for Particle Physics near Geneva, had been producing tremendous amounts of data in the months since it awoke from its winter-long slumber. But the more than 6,000 physicists who work on the LHC's two largest experiments were wary of unintentionally adding biases to their analysis. They had agreed to remain completely unaware of the results, performing what are called blind analyses until mid-June, when all would suddenly be revealed in a frenzy of nocturnal activity. Many of the young scientists worked through that night to untangle the newly freed threads of evidence. Although the LHC is a giant collider feeding multiple experiments, only the two largest ones, ATLAS and CMS, had been tasked with finding the Higgs boson, the long-sought particle that would complete the standard model of particle physics, the theoretical description of the subatomic world. Each massive detector records the subatomic debris spewing relentlessly from proton collisions in its midst. A detailed, independent accounting of these remnants can reveal fleeting new phenomena, including perhaps the elusive Higgs boson. Yet the detectors have to sift through the particle tracts and energy deposits while enduring a steady siege of low-energy background particles that threaten to swamp potentially interesting signals. It is like drinking from a fire hose while trying to ferret out a few tiny grains of gold with your teeth. Fortunately, the scientists knew what they were looking for. After the LHC's disastrous start, an electrical splice between two magnets warmed and melted just 9 days after the LHC came online in 2008, triggering a powerful spark that punctured the surrounding vessel, released tons of helium, and ripped scores of costly superconducting magnets from their mounts. The collider had been collecting reams of data during 2011, enough to pick up an early hint of a Higgs signal. After that run ended in October for its scheduled winter shutdown, Fabiola Giannotti, then spokesperson for ATLAS, and one of us, Tonelli, then spokesperson for CMS, delivered a special seminar to an overflowing audience in the main CERN auditorium. Both detectors independently found suggestive bumps in the data. What's more, these telltale hints of a Higgs boson corroborated one another. Both ATLAS and CMS reported several dozen events above the expected background in which two photons came blazing out with combined energies of 125 billion electron volts, or 125 GeV. GeV is the standard unit of mass and energy in particle physics, about equal to a proton mass. If proton collisions had created short-lived Higgs bosons, they could have decayed into these photons. Each experiment also found a few surplus events in which 4 charged leptons, electrons or muons, carried off similar total energies. These could also have been the result of a Higgs. Such a concurrence of signals was unprecedented. It suggested that something real was beginning to appear in the data. Yet, given the stringent norms of particle physics, none of the signals observed in 2011 were strong enough to allow for claims of a discovery. Data peaks and bumps like this had often proved ephemeral, mere random fluctuations. And the successful spring 2012 run, which generated more proton collisions in 11 weeks than had come in during all of 2011, could easily have washed out the nascent data peaks, smothering them in background noise. Of course, the opposite could occur too. If the bumps were the result of an actual Higgs boson, not just a cruel statistical artifact, all the new data gave researchers a good chance of being able to claim an official discovery, ending this decades-long search and beginning a whole new era in our understanding of matter and the universe. A 3-decade search. Never just another particle, the Higgs boson is the cornerstone